For about 3.2 million years, in what we now call Ethiopia, there's this small figure moving through tall grass near an ancient lake. Not quite like us, not quite like an ape, but something in between. Fast forward to November 24, 1974. Paleoanthropologist Donald Johanson is trudging through the scorching heat of the Hadar region, probably thinking about calling it a day. His pulse quickens. He spots something poking out of a slope, an arm bone. But not just any arm bone. This moment changed everything about our origins. Hey, if you listen to these regularly, subscribe, drop your location and time. Someone from Denver walks their dog to these at 6 a.m. Someone in Barcelona, midnight. Everyone's doing something different. They called her Lucy after that Beatles song playing the night they were celebrating. You know the one, Lucy in the Sky with Diamonds. And Lucy's about to turn our understanding of human evolution completely upside down, because nobody expected this. This tiny individual standing just over a meter tall with a brain about the size of a chimp's was walking upright, like you and me. 2 legs, no knuckles dragging on the ground. Yeah, that's what the scientists thought too. Up until Lucy showed up, everyone assumed our big brains came first, and then we learned to walk. Made sense, right? Big brain equals smart enough to figure out walking, but Lucy threw that whole theory out the window. Her brain was small, really small, about 375 to 500 cubic centimeters. For reference, a modern human brain is about 1,400 cubic centimeters. But those legs? Those legs were built for walking long distances. Lucy belonged to a species called Australopithecus afarensis. Now that's a mouthful, so let's break it down. Australopithecus means southern ape, and afarensis refers to the Afar region where she was found. These weren't humans, you'll recall, not even close, but they weren't apes either. They were something else, something in that fascinating in-between space that tells us so much about where we came from. Lucy wasn't alone, not by a long shot. Just a year after Lucy's discovery, in 1975, the same team found over 200 fossils at the same site. They represented at least 13 individuals, and the team nicknamed them the First Family. Imagine that, a whole group of Australopithecus afarensis individuals, possibly caught in some disaster that buried them all at once. Young and old, males and females, all preserved together. Now it gets really interesting. About 1,500 kilometers away in Tanzania, at a place called Latoli, Mary Leakey's team stumbled onto something that sounds almost too perfect to be real. Footprints, actual footprints, preserved in volcanic ash that hardened like concrete 76 million years ago. 3.6 million years ago. And these weren't bear prints or elephant tracks. These were hominin footprints, probably made by Australopithecus afarensis, showing clear evidence of bipedal walking. The prints showed everything. The heel struck first. Just like when you walk, the big toe was aligned with the other toes, not jutting out to the side like in apes. There was even evidence of an arch in the foot, that critical structure that helps us push off with each step. Someone, or rather several someones, walked across that plain over 3.5 million years ago, and their footsteps were so perfectly preserved that we can still see them today. Think about that for a second. These creatures were walking upright before they had big brains, before they made sophisticated tools, before they did any of the things we associate with being human. They were just walking around, probably gathering food, avoiding predators, living their lives in the African landscape that was slowly shifting from forests to more open grasslands. Her arms were long and powerful, and her finger bones were curved, suggesting she still spent a good amount of time in trees. Makes sense when you think about it. The African savanna was crawling with predators: lions, hyenas, saber-toothed cats. If you can climb a tree to escape becoming someone's lunch, you're going to keep those climbing adaptations around, right? But her pelvis? That told a different story. It was remodeled, restructured to support walking upright. Her thigh bones angled inward toward her knees, exactly like ours do, which prevents the body from swaying side to side when walking. And that spine, it had curves that we have, but chimps don't. Curves that are essential for balancing our weight when we're standing on two legs. So Lucy and her kind were living these dual lives, comfortable on the ground, walking for long distances, but still able to scramble up into the trees when danger came calling. This wasn't some halfway evolution that didn't work. This was a wildly successful adaptation that lasted for over 900,000 years. That's more than 4 times longer than our own species has been around. Let that sink in. We, Homo sapiens, have only been here for about 300,000 years, and we think we're so successful. Australopithecus afarensis was doing their thing for almost 1 million years. And they weren't just surviving, they were thriving. Fossils of this species have been found all over East Africa, Ethiopia, Kenya, Tanzania. They adapted to different environments, from woodlands to grasslands, showing a flexibility that would become a hallmark of our lineage. Their teeth tell us they ate a varied diet: fruits, leaves, seeds, nuts, maybe the occasional small animal. They weren't specialized like some other species we'll talk about. They could adapt, could eat what was available, could survive in changing conditions. But here's a question that keeps scientists up at night. How did they end up fossilized in the first place? Lucy's bones were found scattered across a hillside, and after careful analysis, scientists think she might have died from a fall, probably from a tree, which makes sense given those powerful arms and curved fingers. She was young, probably in her late teens or early 20s by human standards, though fully mature for her species. The bones show she'd given birth at least once. Her wisdom teeth had erupted, another sign of adulthood. Recent studies using high-resolution CT scans found fractures in Lucy's bones that are consistent with falling from a significant height. Her right arm shows compression fractures, the kind you get when you instinctively reach out to break your fall. Her left shoulder was shattered, several ribs were broken. It's a strangely human way to die, reaching out to catch yourself as you fall, a final moment frozen in time by the fossil record. The first family's story is even more mysterious. All those individuals, young and old, buried together at the same place. What happened to them? Flash flood maybe? Disease? We'll probably never know for sure, but their tragedy is our gain, because finding so many individuals from the same species at the same location gave scientists an incredible data set to work with. They could see the variation within the species. Males were significantly larger than females, about 50% bigger in some cases. That's called sexual dimorphism, and it tells us something about their social structure. In primate species where males are much larger than females, it usually means males were competing with each other for access to females. So Australopithecus afarensis probably lived in groups where a few dominant males did most of the mating, kind of like gorillas or chimps today. But here's something that really drives home how different they were from us. Their brains grew fast, really fast. A juvenile Australopithecus afarensis discovered in 2000, nicknamed coelom, showed that these creatures matured quickly, more like chimps than humans. Her teeth erupted in a pattern similar to a 3-year-old chimp's. Modern humans have this extended childhood, this long period where our brains are still developing and we're learning from our parents and community. Australopithecus afarensis didn't have that luxury. Why the rush? Predators. The African landscape was brutal. If you matured faster, you had a better chance of surviving long enough to reproduce and pass on your genes. But here's the twist. While their bodies and teeth matured quickly, their brains showed signs of growing more slowly than their ape cousins. It's like evolution was testing out this new strategy, this balance between maturing fast enough to survive, but slow enough to develop a slightly bigger, more capable brain. Lucy's discovery didn't just give us one individual or one species, it gave us a window into a critical moment in our evolutionary history, a moment when our ancestors were figuring out this whole walking upright thing, when they were adapting to life on the ground while keeping a safety net in the trees. They weren't trying to become human, they weren't working toward anything, they were just living, just surviving, just passing on their genes to the next generation. And yet their success, their nearly million-year run, set the stage for everything that came after, because walking upright freed up our hands, those hands that Lucy used to climb trees, future species would use to make tools, to carry food, to gesture and communicate in more complex ways. That pelvis that remodeled itself for bipedalism, it would keep evolving, keep changing, eventually giving birth to babies with even bigger heads and brains. But Lucy and her kind didn't know any of that. They were just trying to make it through another day in the African Rift Valley, trying to find enough food, trying to avoid becoming food themselves. They were successful in ways we're only beginning to understand, and their legacy is literally written in our bones. Every time you stand up, every time you walk across a room, you're using a body plan that started with creatures like Lucy over 3 million years ago. The story gets even more complicated, though, because while Australopithecus afarensis was doing their thing in East Africa, other hominins were evolving too. Different branches, different experiments in what it meant to be a bipedal ape in Africa. Some had massive jaws for chewing tough vegetation. Others developed slightly bigger brains and started figuring out how to make tools. The human family tree wasn't a straight line from Lucy to us. It was a bush with multiple branches growing, competing, sometimes interbreeding, sometimes going extinct. Lucy represents one incredibly successful branch of that bush, but she wasn't our direct ancestor, at least we don't think so. The relationship between Australopithecus afarensis and early members of our genus, Homo, is still hotly debated. Did one evolve directly from the other? Or did they share a common ancestor that we haven't found yet? These are the questions that make paleoanthropology so fascinating and so frustrating at the same time. What we do know is that by about 2.5 million years ago, something new was showing up in the fossil record. Hominins with bigger brains, hominins who were definitely making and using stone tools, hominins that looked less like Lucy and more like, well, like us. These new arrivals would eventually be classified in our genus, Homo, and they would take that bipedal body plan that Lucy's kind perfected and run with it. Literally run, because some of these new species developed body proportions perfect for long-distance running. But we're getting ahead of ourselves, because before we meet these new characters in our evolutionary story, we need to understand that Lucy and Australopithecus afarensis weren't the only players in the game. While they were walking around Ethiopia, Kenya and Tanzania, other Australopithecines were evolving in different parts of Africa. Some of these species overlapped in time and space with Australopithecus afarensis. They were neighbours, competitors, possibly even occasional meals for the same predators. The African continent from 4 million to 2 million years ago was like this incredible laboratory for evolution, testing out different ways to be a bipedal primate. Some lineages emphasized big teeth and powerful jaws, others experimented with slightly bigger brains. Still, others developed different body proportions or different social structures. Most of these experiments failed, going extinct without leaving any descendants. But a few, a critical few, succeeded in ways that eventually led to us. Lucy's discovery in 1974 was the beginning of understanding all of this. Before her, we had fragmentary evidence, pieces of the puzzle, but not enough to see the bigger picture. Lucy gave us 40% of a skeleton, enough to see how the whole body fit together, how bipedalism actually worked in these ancient creatures. And then the Laetoli footprints confirmed it, removing any doubt that these creatures were walking upright over 3.5 million years ago. The impact on the scientific community was massive. Suddenly we had to rethink everything. Big brains didn't come first. Walking upright did. And if walking upright came first, then all our theories about why we evolved to walk upright needed revision. Was it to see over tall grass, to carry tools or food, to travel longer distances more efficiently, to keep cool by exposing less of our body to the direct sun? Probably all of the above, plus factors we haven't even thought of yet. And here's the really mind-blowing part. Every bipedal hominin that came after Australopithecus afarensis, including us, is using a body plan that was essentially figured out by Lucy's time. Sure, it got refined, modified, improved, our legs got longer, our pelvis changed shape, our feet lost those curved toes, but the basic blueprint, the fundamental mechanics of walking on two legs that was established over 3 million years ago by creatures with brains 1/3 the size of ours. So when we look at Lucy, when we see those reconstructed bones in a museum or pictures in a textbook, we're not just looking at an ancient fossil, we're looking at a revolutionary. Not in any intentional sense, she wasn't trying to change the world, but her kind, through the simple act of walking upright, set in motion a chain of events that would eventually lead to every human who has ever lived. That's the power of deep time, of evolution, of these small changes accumulating over millions of years until suddenly you've gone from a small-brained bipedal ape in Africa to humans walking on the moon. But Lucy's story is just the beginning, because while Australopithecus afarensis was perfecting the art of walking upright, other changes were happening, other species were emerging, and the stage was being set for the next chapter in human evolution, a chapter that would see the emergence of our genus, Homo, and with it, bigger brains, better tools, and the first migrations out of Africa into the wider world. Around 2.5 million years ago, something shifted in the African landscape. The climate was getting drier, forests were giving way to more open grasslands, and a new player was about to enter the evolutionary game. The earliest members of our genus, Homo, were showing up in the fossil record, and they brought something revolutionary with them. Tools, actual manufactured stone tools that required planning, skill, and a level of intelligence we hadn't seen before. It gets complicated, I mean really complicated. When Louis and Mary Leakey started digging at Olduvai Gorge in Tanzania back in the 1960s, they found something that stumped everyone. Alongside these crude stone tools, they found fossil bones of a hominin that didn't quite fit any category they knew. It had a slightly bigger brain than the Australopithecines, about 510 to 600 cubic centimeters. Its teeth were smaller, more human-like, but it still had long arms and a face that jutted out more than ours does. They decided to call it Homo habilis. handyman, because they figured, hey, we found it near all these tools, it must be the one making them, right? And by putting this creature in our genus, in Homo, they were essentially saying, this is one of us. This is on the direct line to modern humans. But does this hominin really belong in our genus? Was it more like us than its earlier ancestors? The fossils they found at Olduvai were fragmentary at first. Some teeth, a lower jaw, parts of a skull, hand bones from what they called Olduvai hominid 7. The individual was young, maybe in their early teens when they died. Those hand bones were fascinating though, because they suggested this creature could form a precision grip. The ability to touch your thumb to your fingertips that's crucial for making and using tools. Apes can't really do that. We can. And apparently Homo habilis could too. More discoveries kept coming. In 1968 they found another skull, nicknamed Twiggy because it had been trampled by cattle and was crushed into hundreds of tiny fragments before fossilization. Poor thing had to be painstakingly reconstructed piece by piece. Then there was OH13, found in 1963, which gave them a better look at the face and teeth, and OH24, discovered later, which showed just how small and primitive some of these individuals were. The problem that started becoming obvious as more fossils turned up, there was a lot of variation, like a suspicious amount of variation. Some specimens had bigger brains, others smaller, some had longer faces, others shorter. The teeth varied significantly in size. It's like they were finding fossils from different species but calling them all Homo habilis, and maybe that's exactly what was happening. In 1972, Richard Leakey's team found a skull at Lake Turkana in Kenya that really threw a wrench into everything. They labelled it KNM-ER1470, and this thing was different. It had a much bigger brain than typical Homo habilis specimens, about 775 cubic centimetres, way over the 600 cubic centimetre cutoff that everyone was using to define our genus. Its face was longer and flatter, its premolars and canines were larger. It looked like it could be Homo habilis, but it also looked like it might be something else entirely. So in 1986 and then again in 1992, scientists took another look at KNM-ER1470 and said, you know what, this isn't Homo habilis, this is its own species. They called it Homo rudolfensis, after Lake Rudolph, the old name for Lake Turkana. Now we had two species of early Homo living in East Africa at roughly the same time, around 1.8 to 1.9 million years ago. But wait, there's more. While all this was happening, paleontologists were finding fossils of hominins that didn't fit neatly into either category. Some looked like they might be transitional between Australopithecines and Homo. Others seemed to show a mix of features from different species. The human family tree was starting to look less like a tree and more like a tangled bush with branches going every direction. The tools at Olduvai Gorge, the ones that gave Homo habilis its name, are called Oldowan tools. They're the earliest type of manufactured stone tools we know about, dating back to about 2.6 million years ago. And they're pretty simple. You take a cobble, a nice round rock, and you use another rock as a hammerstone to knock flakes off it. Those sharp flakes can be used for cutting and scraping, and the core that's left over can be used as a chopper. Sounds easy, but it's not. You have to understand which rocks will flake properly. You need to hit at the right angle with the right amount of force. It requires hand-eye coordination, planning, and understanding of cause and effect. This isn't random behavior. This is cognitive ability in action, and whoever was making these tools, whether it was Homo habilis or some other species, they were doing something no other creature on Earth was doing at the time. Except here's the thing that really complicates the story. We now know that stone tools show up in the archaeological record before Homo habilis does. 3.3 million year old tools have been found in Kenya. That's way older than any Homo fossil we've discovered. So if Homo habilis wasn't making those earliest tools, who was? Maybe some advanced Australopithecine, maybe an early Homo species we haven't found yet. Or maybe, and this is the really intriguing possibility, maybe different hominin species were all figuring out stone tools independently. Maybe it wasn't some unique spark of genius in one species, but rather a threshold that multiple lineages crossed once their brains got big enough and their hands got dexterous enough. The more we dig, literally and figuratively, the messier the picture becomes. In 2023, scientists reported finding Oldowan tools at a site in Kenya, alongside fossils of Paranthropus, a heavily built hominin with massive jaws and huge molars for grinding tough vegetation. Paranthropus and Homo were different lineages, and Paranthropus was always thought to be this specialized dead end that just munched on roots and tubers all day. But here they were, apparently making tools too, or at least hanging out in the same places where tools were being made. So, who was making tools? Maybe everyone was. Maybe once you're bipedal, once you've got hands free from walking, once your brain reaches a certain size, tool use becomes almost inevitable. It's not that one species invented it and passed it down. Multiple species might have been doing it, each in their own way, each figuring out that, hey, a sharp rock is better than trying to tear meat apart with your teeth alone. The debate about Homo habilis isn't just about one species, it's about how we define our genus, how we decide who gets to be called Homo and who doesn't. For a long time, scientists used a checklist approach. To be Homo, you needed a brain over 600 cubic centimeters. You needed certain body proportions, you needed to use tools, maybe you needed the capability for language. But then fossils started breaking all these rules. The Dmanisi fossils from Georgia, which we'll get to in a minute, had some individuals with brains under 600 cubic centimeters, but they still looked like early Homo erectus. Homo habilis might have used tools, but so might have Australopithecines and Paranthropus. Language capabilities can't really be determined from fossils, so that criterion is pretty useless. And body proportions? Turns out there was way more variation in early Homo than anyone expected. It's like trying to define where a mountain begins. Everyone can point at the peak and say, that's definitely the mountain. And everyone can point at the flat ground far away and say, that's definitely not the mountain. But where exactly does the mountain start? Is it at a certain elevation? A certain slope? There's no obvious line. And trying to draw one is kind of arbitrary. Same with our genus. We can look at modern humans and say, definitely Homo. We can look at Australopithecines and say, definitely not Homo. But Homo habilis, Homo rudolfensis, these early primitive species that don't quite look like us, but also don't quite look like Australopithecines? That's where it gets fuzzy, and scientists love to argue about fuzzy boundaries. Some researchers have suggested kicking Homo habilis out of our genus entirely, put it back with Australopithecus, they say, or give it its own new genus. It's too primitive, too ape-like in too many ways. Its brain isn't big enough, its body proportions are wrong, it doesn't deserve to be called Homo. Others argue that we should keep the genus broad and inclusive. Evolution doesn't happen in clean jumps. There's always going to be transitional species that blur the lines. If we kick out every species that doesn't look exactly like the later members of Homo, we're going to miss the crucial evolutionary steps that got us from Australopithecines to modern humans. And then there's the question of who Homo habilis's ancestors and descendants were. Some scientists think it evolved from Australopithecus afarensis, or a close relative. Others point to different Australopithecine species as the likely ancestor. As for descendants, did Homo habilis give rise to Homo erectus, the next big success story in human evolution? Or was it Homo rudolfensis that did that? Or did both species contribute to later Homo, maybe even interbreeding and mixing their genes? The fossil record is maddeningly incomplete. We have snapshots, not movies, a bone here, a skull there, stone tools scattered across ancient landscapes. We're trying to reconstruct millions of years of evolutionary history from these fragments, and it's no wonder we can't agree on the details. What we can say is that between 2.5 and 1.5 million years ago, there were multiple hominin species living in Africa. Some were Australopithecines, still following that successful body plan that had worked for millions of years. Others were early members of Homo, experimenting with bigger brains and better tools. They were all competing for resources, all trying to survive in an environment that was constantly changing. Climate swings were brutal during this period. Ice ages in the northern hemisphere meant Africa was getting cooler and drier. Forests shrank, grasslands expanded, species that were adapted to forest life struggled, species that could adapt to more open environments thrived. The ones with bigger brains, the ones who could figure out new food sources and new ways to avoid predators, they were the ones who made it. Homo habilis, or whatever we want to call these early members of our genus, were generalists. Their teeth suggest they ate a variety of foods: fruits, leaves, tubers, insects, meat when they could get it. They weren't specialized for one type of food like Paranthropus was, and that flexibility, that ability to adapt, might be the real reason they belong in our genus, regardless of their brain size or exact body proportions. Because that's what our lineage does, right? We adapt, we figure stuff out, we use tools and intelligence to overcome physical limitations. Modern humans aren't the strongest or fastest or toughest animals. We don't have claws or fangs or thick hides. What we have are brains that can solve problems and hands that can manipulate objects with incredible precision. And those traits, those fundamental characteristics of being human, they started showing up in species like Homo habilis 2.5 million years ago. The stone tools tell us these early Homo individuals were thinking ahead. They weren't just picking up rocks randomly. They were selecting specific types of stone that would flake properly. They were carrying rocks from one location to another, sometimes over several kilometers. That's planning. That's anticipating future needs. That's a level of cognitive ability that goes beyond what we see in modern apes. And the butchery marks on animal bones tell us they were processing meat. Whether they were hunting or scavenging is still debated, probably both, opportunistically. A lot of the bones show carnivore teeth marks alongside stone tool cut marks, suggesting these hominins were scavenging from kills made by lions or hyenas. They'd wait for the big predators to finish, then move in with their tools to strip off whatever meat was left and crack open bones to get at the nutritious marrow inside. Not glamorous, but effective, and in the harsh environment of Pleistocene Africa, you took calories where you could find them. There's evidence that Homo habilis might have had some form of communication beyond what apes have. Their brain anatomy suggests slightly more developed language areas. Not modern human language, but maybe something between ape vocalizations and actual speech. They were social creatures, living in groups for protection and cooperation. Group size estimates based on brain size suggest maybe 70 to 85 individuals, similar to modern chimp and baboon groups. Living in groups that size requires social intelligence. You need to remember who's who's dominant, who you can trust, who might steal your food. You need to cooperate for defense against predators. You probably need some form of communication to coordinate activities, to warn others about danger, to share information about food sources. These weren't solitary creatures. They were social, and being social pushed their intelligence even higher. But despite all these advances, despite bigger brains and tools and social cooperation, Homo habilis never left Africa. All their fossils come from East and possibly South Africa. They didn't migrate out into Eurasia like their descendants would. Maybe they weren't quite advanced enough yet. Maybe their tools weren't sophisticated enough for them to survive in new environments. Or maybe they just didn't need to. Africa had everything they needed, and they were successful enough that expansion wasn't necessary. Or maybe they did try to expand, and we just haven't found the fossils yet. That's always a possibility in paleontology. Absence of evidence isn't evidence of absence. The fossil record is incredibly patchy, and we're finding new sites all the time that rewrite what we thought we knew. What we do know is that by about 1.9 million years ago, a new species was showing up. Homo erectus, taller, with longer legs and shorter arms, even bigger brains, averaging around 900 to 1,000 cubic centimeters, more human-like body proportions, better tools. And, most importantly, Homo erectus did something Homo habilis never managed. They left Africa and spread across Eurasia, reaching as far as China and Indonesia. Were Homo erectus descendants of Homo habilis, or Homo rudolfensis, or some other early Homo species we haven't discovered yet? The evidence is contradictory and incomplete. Some scientists think yes, Homo erectus evolved directly from Homo habilis in Africa, then spread outward. Others think the relationship is more complicated, with multiple early Homo species contributing genes through interbreeding. And then there are those Dmanisi fossils from Georgia dating to about 1.77 million years ago. These individuals are fascinating because they show so much variation. Some skulls have big brows and look very Homo erectus-like, but their brains are small, down in the Homo habilis range. Their bodies are short and lightly built. They look primitive in many ways, but they're found outside of Africa, which supposedly only Homo erectus was supposed to do. Did these Dmanisi hominins represent the earliest wave of Homo erectus leaving Africa? Were they some intermediate species between Homo habilis and classic Homo erectus? Some scientists have argued that all these early species, Homo habilis, Homo rudolfensis, Homo erectus, they're all actually just one species showing a lot of variation, like how modern humans show variation. Put a tall Norwegian next to a short San individual from South Africa, and they look quite different, but they're the same species. But other scientists look at the specific details of the skulls and teeth and say, no, these are distinct species with distinct evolutionary adaptations. The variation is too great to all fit under one species label. Round and round the debate goes, and it probably won't be settled anytime soon. We need more fossils. We need fossils from more time periods and more locations. We need complete skeletons so we can see how all the body parts fit together. We need DNA, but ancient DNA degrades quickly in the African heat, so we're unlikely to ever get genetic material from these early species. What we're left with is bones and stones and a whole lot of educated guessing. But that's the beauty and the frustration of paleoanthropology. Every new fossil changes the story. Every new technique reveals something we couldn't see before. The quest to understand where we came from is ongoing, and we're nowhere near the end of it. 1.9 million years ago, everything changed. A new kind of hominin emerged that would dominate the old world for over 1.5 million years. Homo erectus, upright man, and upright they were, with body proportions eerily similar to our own. These weren't the short, long-armed, somewhat ape-like creatures that came before. Homo erectus looked, from a distance anyway, human. The first fossils were discovered way back in 1891 on the Indonesian island of Java by a Dutch anatomist named Eugène Dubois. He found a skull cap, a molar, and a thigh bone near a village called Trinil, and he knew immediately he'd found something big. He named it Pithecanthropus erectus, ape man who stands upright, though that name didn't stick. Later, scientists realized this creature deserved to be in our genus, Homo, and the name was changed to Homo erectus. For decades, scientists thought human evolution happened in Asia, that Asia was the cradle of humanity, because that's where the fossils were turning up. Java man, then later Peking man from caves near Beijing. It wasn't until the mid-20th century that enough African fossils were found to convince everyone that no, actually, we evolved in Africa first and then spread outward. Homo erectus changed the game in so many ways. Let's start with their bodies. They were tall, at least by early hominin standards. Males might have reached around 5 feet 9 inches, females around 5 feet 3 inches. Their legs were long relative to their arms, giving them efficient striding gaits perfect for covering long distances. That matters when you're living in increasingly open habitats where food sources are spread out and you need to travel between water sources. Their rib cages were narrower, more barrel-shaped like ours rather than the funnel shape of Australopithecines. That means their guts were smaller. Smaller guts mean they needed higher quality food that was easier to digest, less time chewing tough vegetation, more time doing other things, like making better tools, like travelling, like figuring out how to survive in diverse environments. And their brains, oh boy, their brains. Ranging from about 800 to over 1100 cubic centimetres, depending on the individual and the time period. That's approaching the lower range of modern human brain size, and it's nearly double what Homo habilis had. Whatever evolutionary pressures were pushing hominin brains bigger, Homo erectus really responded to them. Brain size comes with costs, though. Big brains require a lot of energy. About 20% of your caloric intake goes to feeding your brain, even though it's only about 2% of your body weight. So you need a reliable, high-quality food source to support a big brain. For Homo erectus, that meant meat. Not exclusively, they definitely ate plant foods too, but meat became a much more important part of their diet. And to get meat, you need tools. Homo erectus took stone tool technology to the next level with something called Acheulean hand axes. These weren't the simple choppers and flakes of the older one tradition. Acheulean tools were carefully shaped on both sides, bifacial, creating elegant teardrop shapes with sharp edges all around. Making one of these required planning multiple steps ahead, understanding the three-dimensional structure of the stone, having the fine motor control to remove flakes precisely. These hand axes worked for everything: butchering animals, processing plants, digging, scraping hides, maybe even throwing as weapons, and Homo erectus made them the same way, with the same basic design, for over 1 million years. That's cultural transmission on a scale we haven't seen before. Young individuals learning from adults how to make these tools, passing down knowledge from generation to generation. But the real game changer was fire. Homo erectus is the first hominin species where we have solid evidence of controlled fire use, not just stumbling onto a lightning-struck tree and taking advantage of it, but actually maintaining fires, possibly even making them. The evidence isn't completely clear-cut for the earliest periods, but by around 700,000 years ago, we've got fire sites associated with Homo erectus in multiple locations. Fire changes everything. Cooked food is easier to digest and provides more usable calories. It kills parasites and bacteria, making meat safer to eat. Fire provides warmth, extending the range of habitats you can survive in. It keeps predators away at night. It provides light, extending the useful hours of the day. And sitting around a fire, that's a social thing. That's where stories get told, knowledge gets shared, bonds get strengthened. With these adaptations, Homo erectus wasn't limited to warm African environments anymore. They could handle cooler climates, they could adapt to different food sources, they could learn and problem solve in ways that let them survive almost anywhere, and that's exactly what they did. They left Africa and spread across Asia in what might have been multiple waves of migration. The earliest evidence of Homo erectus outside Africa comes from Dmanisi in the country of Georgia, dated to about 1.77 million years ago. This site is remarkable because it's given us 5 well-preserved skulls plus over 100 other bones, all from the same general location and time period, and the amount of variation in those skulls is incredible. Skull 5 from Dmanisi is particularly interesting. It has a tiny brain, just 546 cubic centimeters, smaller than some Homo habilis specimens. Its face is large and projects forward significantly. Put the face and the brain case together and they look like they should belong to different species, but they don't. They're from the same individual, and they're definitely from the same population as the other, more typical-looking Homo erectus skulls found at the site. What does this tell us? Maybe that early Homo erectus populations had way more variation than we've been giving them credit for. Maybe that brain size isn't as important for defining species as we thought. Maybe that some of those supposedly different species from Africa, Homo habilis and Homo rudolfensis, maybe they're all just variants of the same lineage that would eventually become Homo erectus. Or maybe the Dmanisi population represents an earlier migration, a more primitive form of Homo erectus that got out of Africa before the species was fully developed. Maybe evolution continued happening in Africa while this Georgian population was isolated, leading to the more classic Homo erectus forms we see later. The debate isn't settled and probably won't be for a while, but what's clear is that by 1.77 million years ago, hominins had made it to the southern edge of Eurasia and were successfully surviving there despite having relatively small brains and primitive features. From Georgia, the trail of Homo erectus fossils and tools leads eastward. By 1.6 to 1.7 million years ago, they'd reached China. Stone tools found at Shangcheng in China might be even older, possibly over 2 million years old, though whether those were made by Homo erectus or some earlier hominin is uncertain. And by 1.6 million years ago, they'd made it all the way to Java in Indonesia, over 12,000 kilometers from East Africa. That's an incredible journey. It probably happened slowly, over many generations, populations gradually expanding into new territories. They weren't exploring in any intentional sense. They were just following game, finding new food sources, moving into unoccupied niches. But the result was a species that spread across 2 continents, adapting to deserts and forests and grasslands and temperate zones. China has yielded particularly rich Homo erectus fossil sites. The caves at Zhoukoudian near Beijing, where Peking man was found, contained fossils from multiple individuals spanning hundreds of thousands of years. Tragically, most of those original fossils were lost during World War II, but casts and descriptions remain. Other sites at Lantian, Hexian, and elsewhere have added to our understanding of Asian Homo erectus. Java has been even more productive. Sites at Sangiran, Ngandong, and other locations have produced dozens of fossils spanning from 1.6 million years ago to possibly as recent as 143,000 years ago. That's right, Homo erectus might have survived on Java until fairly recently in evolutionary terms, long after more advanced humans had evolved in Africa. Asian Homo erectus tended to be more robust than their African counterparts. Thicker skull bones, more pronounced brow ridges, larger faces. Whether this represents a separate species or just regional variation is, you guessed it, another point of debate. Some scientists separate African Homo erectus into its own species, Homo ergaster, while keeping the Asian fossils as Homo erectus. Others lump them all together as one highly variable species. What about Europe? Homo erectus was slower to reach Europe, and the evidence there is more scattered. The earliest possible European sites are controversial, with some claimed dates around 1.4 million years ago that not everyone accepts. What's clear is that Europe was harder to colonize, probably because of the colder climate and different ecosystems. It took more advanced adaptations to survive European winters. But the question everyone wants answered is, why did Homo erectus leave Africa in the first place? What drove them to migrate into unknown territories? Climate change is probably a big part of the answer. Between 2 and 1.5 million years ago, Earth's climate was fluctuating wildly. Africa was experiencing cycles of wet and dry periods. During wet periods, the Sahara became greener, creating corridors that animals, including hominins, could use to move north. During dry periods, resources in East Africa would have been scarcer, pushing populations to expand their ranges in search of food. Following animal migrations makes sense too. Large herbivores like elephants and antelopes have seasonal migration patterns. If Homo erectus was scavenging from predator kills or learning to hunt, following herds would put them in the right place for food sources. And if you're following herds, eventually you end up far from where you started. Homo erectus also had the tools and intelligence to adapt to new environments quickly, encountering a new type of plant, figure out if it's edible, see an unfamiliar animal, learn its behavior, figure out how to hunt or scavenge it. This behavioral flexibility is key. Earlier hominins were probably too specialized, too dependent on specific African resources to survive migration. Homo erectus had crossed a cognitive threshold that made them adaptable enough to succeed almost anywhere. There's also the possibility of competition driving migration. If multiple hominin species are competing for the same resources in East Africa, some populations might get pushed into marginal habitats, and from marginal African habitats it's not such a big jump to non-African habitats. You're already adapted to less than ideal conditions, so trying somewhere completely new isn't as big a risk. Whatever the specific triggers, the result was that Homo erectus became the first truly widespread hominin. They occupied a range that extended from South Africa to northern China, from Indonesia to possibly the Middle East and southern Europe. No other hominin species before them had achieved anything close to that geographic distribution. And they lasted. Homo erectus appears in the fossil record around 1.9 million years ago and persists until at least 200,000 years ago in most regions, with those possible late survivors in Java hanging on even longer. That's over 1.5 million years of existence. For comparison, modern Homo sapiens has only been around for about 300,000 years. We've got a long way to go before we match Homo erectus's success in terms of longevity. During their long run, Homo erectus saw a lot of evolutionary change. Early Homo erectus from Africa and Dmanisi were relatively small-brained and primitive. Later, Homo erectus from China and Java had larger brains, more robust builds, and probably more sophisticated behaviors. This was a species that was still evolving, still adapting, not some static form frozen in time. There's evidence for some surprisingly advanced behaviors too. that elderly individual from Dmanisi who'd lost most of his teeth long before death, suggests his group was caring for him, feeding him soft foods, keeping him alive despite his inability to chew. That's compassion, social bonding, the kind of behaviour we usually associate with more modern humans. Sites in Spain, though controversial in their dates, might show evidence of Homo erectus building simple shelters. A circle of stones at Olduvai Gorge has been interpreted as possibly supporting poles for a windbreak or crude hut, though this is debated. If true, it would be the earliest evidence of architecture, of humans modifying their environment to make shelter rather than just using natural caves or overhangs. And while we're not certain about language abilities, Homo erectus almost certainly had more complex communication than earlier hominins. Making Acheulean tools requires teaching and learning. Coordinating hunts or scavenging requires communication. Living in social groups and maintaining fire requires cooperation that probably needed something beyond simple gestures and grunts. Their success set the stage for everything that came next. Later, human species, including Homo heidelbergensis, Homo neanderthalensis, and eventually Homo sapiens, all evolved from Homo erectus populations. We're the descendants of these ancient migrants who left Africa and made the whole world their home. But Homo erectus wasn't the only hominin species around during this period. Back in Africa, while some populations were heading out into Eurasia, others stayed behind and continued evolving. Different experiments were happening, different evolutionary pathways were being tried. Some led to dead ends. Others led to us. And understanding that diversity, that bush of different species all competing and coexisting, that's crucial to understanding where we came from. While Homo erectus was conquering Asia, back in Africa there was this whole other drama playing out. Different hominin species were competing for resources, adapting to changing environments, and sometimes just straight up going extinct. The African landscape between 2 and 1 million years ago was like a testing ground for different ways to be an upright walking primate, and not all experiments worked out equally well. Take Paranthropus, for example. These guys went in a completely different direction from the Homo lineage. Instead of getting slightly bigger brains and better tools, Paranthropus doubled down on powerful jaws and massive teeth. We're talking molars that are 3 to 4 times the size of yours, with thick enamel that could grind through the toughest plant materials. Their skulls had these pronounced sagittal crests on top, like a bony mohawk, where enormous jaw muscles attached. Paranthropus boisei, found at Olduvai Gorge and other East African sites, was nicknamed Nutcracker Man because of those ridiculous teeth. Scientists initially thought these creatures were just munching on nuts and hard seeds all day long, but when they did microscopic analysis of the tooth wear patterns, surprise, the evidence suggested they were actually eating a lot of soft foods, grasses, sedges, maybe papyrus. They had the dental equipment for a tough diet as a backup, but day to day they were probably eating whatever was abundant and easy to get. And get this, Paranthropus boisei lived from about 2.3 to 1.2 million years ago. That's over 1 million years of success. They coexisted with Homo habilis and early Homo erectus for hundreds of thousands of years. Same landscapes, same time periods, completely different survival strategies. Paranthropus stayed specialized for tough, low-quality plant foods. Homo went the direction of bigger brains, better tools, and more meat eating. Guess which strategy won in the long run? Well, you're here and Paranthropus isn't, so that tells you something, but for a long time it wasn't obvious which approach would be more successful. Paranthropus was perfectly adapted to their niche. They could survive on foods that other species couldn't process. During dry periods when preferred foods were scarce, having the ability to fall back on really tough fibrous plants was a huge advantage. So why did they go extinct? Climate change probably played a role. As Africa got drier and grasslands expanded, the specific plant communities Paranthropus depended on might have shrunk. They were specialists, you'll recall, and specialists are vulnerable when their environment changes. Homo species, with their more flexible diets and tool-using abilities, could adapt to new conditions more easily. There's also the possibility of competition. If Homo and Paranthropus were competing for the same resources, even partially, the smarter, more adaptable species is going to have an edge, not through direct conflict necessarily, but just through being able to exploit resources more efficiently. Over enough generations, that adds up. Paranthropus wasn't the only robust Australopithecine either. Paranthropus robustus in South Africa and Paranthropus ethiopicus in East Africa were related species with similar specializations. The whole Paranthropus lineage represents this alternative evolutionary pathway that hominins tried, and it worked for over 1 million years before finally dying out. Now, while all this was happening, there's another species that throws a wrench into everything. Australopithecus sediba, found in South Africa and dating to about 1.98 million years ago. This one's fascinating because it has a weird mix of features. Small brain and long arms like Australopithecines, but small teeth and facial features that look more Homo-like. The scientists who discovered it in 2010 think it might be more closely related to our genus than other Australopithecines are. Maybe it's a direct ancestor of early Homo, they said. But other experts looked at the dates and went, wait, this is too recent. By the time Australopithecus sediba was around, Homo was already established. It can't be an ancestor if it shows up after the descendants already exist. Unless, and this is where it gets speculative, unless Australopithecus sediba represents a surviving population of whatever gave rise to early Homo, like maybe the transition from Australopithecus to Homo happened earlier than we've found fossils for, and Australopithecus sediba is a late surviving branch of that ancestral population. It's possible, but we'd need more evidence to say for sure. The fact that this is even a debate shows how messy human evolution is. We want a clean family tree with clear ancestors and descendants, but what we actually have is a tangled bush with branches crossing, populations mixing, and lots of missing pieces that may never be found. This brings us to the big question that's been haunting paleontology for 60 years. What actually defines our genus? What makes something Homo rather than Australopithecus? When the Leakeys first proposed putting Homo habilis in our genus back in 1964, they used criteria that seemed reasonable at the time. Upright posture, bipedalism, ability to make tools. Check, check, and check. But then Lucy came along and showed that Australopithecines were already bipedal. The Laetoli footprints proved it beyond doubt, so bipedalism alone can't define Homo. And then we found evidence that Australopithecines and Paranthropus might have been making tools too, so tool use alone doesn't work either. Okay, fine, scientists said. Let's use brain size. To be Homo, you need a brain over 600 cubic centimeters. That makes sense because bigger brains mean more intelligence, more cognitive ability, more of what makes us human. Except then the Demonisi fossils showed up with skulls under 600 cubic centimeters, but clearly Homo erectus-like features, and some Australopithecus afarensis individuals had brain sizes overlapping with small Homo habilis specimens. So brain size alone doesn't define the boundary clearly either. What about body proportions? Homo species have longer legs relative to their arms compared to Australopithecines. That's true for Homo erectus and later humans, but Homo habilis had relatively long arms and short legs, more like Australopithecines. And some Australopithecines had relatively long legs, more like early Homo. Language capability? Can't determine that from fossils, not reliably anyway. Diet quality? Hard to measure, and there's probably overlap between late Australopithecines and early Homo. Cultural complexity. Define cultural complexity in a way that's measurable from archaeological sites, millions of years old. Good luck with that. Every criterion scientists have tried to use to define our genus has exceptions, fuzzy boundaries, problematic cases. It's like the mountain analogy again. Where does the mountain actually begin? There's no single obvious line, and trying to draw one involves arbitrary choices. Some researchers have proposed tooth size as a defining feature. Smaller teeth indicate higher quality diets and more food processing with tools, freeing up dental real estate that used to be needed for heavy chewing. As hominins started eating more meat and cooking their food, they needed smaller, less robust teeth. So maybe the transition to Homo is marked by a significant reduction in tooth size. That's an interesting idea, but it's got problems too. Tooth size varies a lot within species. Males and females have different sized teeth. Different populations adapted to different diets might show different tooth proportions. Drawing a line based on tooth size means picking some arbitrary measurement and saying anything above this is Australopithecus, anything below is Homo. But evolution doesn't work in neat categories like that. Another proposed criterion is developmental pace. Modern humans have really long childhoods compared to apes. We have extended periods of brain growth and learning, which requires parental investment and social support. If we can track growth patterns in fossils by studying microscopic features of teeth, maybe we can see when hominins started shifting toward human-like developmental patterns. Early work suggests Australopithecus had relatively fast development, more like apes. Some early Homo specimens show evidence of slightly slower development, more like us, but again, it's not a clean break. It's a gradual trend with lots of variation, and developmental patterns can be influenced by lots of factors beyond just evolutionary lineage, like nutrition and environmental stresses. In 2015, some frustrated scientists basically said, you know what, let's just start over. Let's look at all the fossils we have with fresh eyes and no preconceptions about which species fit where. Let's decide based on the totality of evidence which traits are actually important for defining what's human versus what's not. It's a nice idea in theory, but in practice, different scientists looking at the same evidence still come to different conclusions because they weight different features differently. The truth is, the boundary between Australopithecus and Homo probably doesn't exist as a clean line because that's not how evolution works. Evolution is gradual. Populations change slowly over generations. At some point, descendants are different enough from ancestors that we'd call them a different species, but there's no moment where Australopithecines gave birth to Homo. It was a continuum. This creates problems for taxonomy though, because taxonomy requires discrete categories. You can't have a species called mostly Australopithecus but kind of getting Homo-like. You have to pick a name and stick with it, even though the reality is messy and gradient. So what do we do with Homo habilis? Opinions are all over the map. Some scientists say keep it in Homo because it shows clear trends toward larger brains and smaller teeth, even if it's still primitive in other ways. It represents an important evolutionary stage, they argue, and removing it from our genus would obscure that. Others say kick it out, put it back with Australopithecus, or give it its own new genus. It's too primitive, too many of its features are Australopithecine-like. We're blurring the definition of Homo by including something that doesn't really fit. Still others say maybe Homo habilis isn't even one species. Maybe we've been lumping together fossils that actually represent two or more different species, some of which belong in Homo and some of which don't. The variation within what we call Homo habilis is suspiciously large. Maybe KNM ER 1470 and the specimens like it, which became Homo rudolfensis, are the real early Homo. And maybe the smaller-brained specimens that look more primitive are actually late Australopithecines. And then you've got the lumpers who say actually maybe all these early species are just one species with a lot of variation. Homo habilis, Homo rudolfensis, early Homo erectus. Maybe they're all Homo erectus, showing geographic and temporal variation. Look at modern humans, the lumpers say. We show huge variation in brain size, body proportions, facial features, but we're all one species. Maybe ancient humans showed similar variation, and we're just not recognizing it because we're used to seeing them as fossils separated in time and space. The Dmanisi fossils give some support to the lumper interpretation. 5 skulls from the same place and time, and they're wildly different from each other. Different sized brains, different facial proportions, different everything. If we'd found those skulls at 5 different sites across Africa, we might have called them 5 different species, but they're from one population, which means a single hominin population can show that much variation. So maybe we've been oversplitting. Maybe there weren't a dozen different species of early Homo bouncing around Africa and Eurasia. Maybe there were only a few species, or even just one highly variable species that changed over time and looked different in different regions. But the splitters push back hard on that. They point to specific anatomical differences, measurable distinctions in skull shape, tooth morphology, limb proportions. These aren't just individual variation, they say. These are evolutionarily significant differences that indicate separate lineages adapting to different environments or niches. Lumping everything together erases real evolutionary diversity and makes it harder to understand what was actually happening during this critical period. Round and round the debate goes, paper after paper, conference after conference, with no resolution in sight. And honestly, maybe that's okay. Maybe the fact that we can't agree shows that we're asking the wrong question. Instead of arguing about which species belongs in which genus, maybe we should focus on understanding the actual evolutionary processes at work. How did brains get bigger? What environmental pressures drove tool use? How did body proportions change over time? Those are questions we can potentially answer with evidence, even if we can't agree on where to draw taxonomic boundaries. What's clear is that between 3 and 1 million years ago, something remarkable happened in Africa. Multiple hominin lineages were experimenting with bipedalism, with diet, with intelligence, with social structures. Most of those experiments failed, leaving no descendants. But one lineage, the one that led to Homo erectus and eventually to us, found a winning combination. Bigger brains, flexible diets, tool use, social cooperation, behavioral adaptability. That lineage didn't succeed because it was trying to become human. It wasn't working toward anything. Natural selection doesn't have goals, but generation after generation, the individuals who were slightly smarter, slightly better with tools, slightly more adaptable, they survived and reproduced at higher rates. And over hundreds of thousands of years, those slight advantages accumulated until you had a species that could migrate across continents, survive in diverse environments, and eventually develop language, art, and civilization. But we're getting way ahead of the story, because before any of that could happen, before humans could spread across the world and become the dominant species, there were still millions of years of evolution ahead. Homo erectus was successful, but they weren't done evolving. New species would emerge from those erectus populations. Some would thrive, others would die out, and eventually, maybe 300,000 years ago, one lineage in Africa would give rise to Homo sapiens, us. Let's talk about what it actually meant to be alive as one of these early humans, not just the bones and fossils, but the daily reality of existence in Pleistocene Africa and Eurasia. Understanding the behaviors, the culture, the cognitive abilities, that's where we start to see the gap between apes and humans beginning to open up. Stone tools, you'll recall, are our best window into the minds of early humans. Every stone tool is a snapshot of someone's decision-making process frozen in rock, and the evolution of stone tool technology over 2.5 million years is basically a timeline of increasing cognitive sophistication. The earliest Oldowan tools, remember, were pretty simple. Take a rock, hit it with another rock, use the sharp flakes that come off. The cores that remained could be used as choppers. These tools required understanding cause and effect. Sure, you had to know that hitting one rock with another in a certain way would produce sharp edges. You had to be able to recognize which types of stone would flake properly. That's not nothing. Modern apes don't do that. But Oldowan tool making doesn't require a lot of advanced planning. You can make these tools pretty quickly, right at the location where you need them. Find a suitable cobble, make your tool, use it, move on. The archaeological sites show exactly that pattern. Scatters of stone tools and animal bones at locations where early humans were processing food, not evidence of long-term planning or transportation of tools over long distances. Acheulean tools, those teardrop-shaped hand axes that Homo erectus made, represent a cognitive leap. Making one requires more steps, more planning. You have to envision the final form you're trying to create and work toward it, removing flakes systematically from both sides of the stone to achieve that symmetrical shape. You're not just making random sharp edges anymore, you're crafting a specific tool design. And Homo erectus made these hand axes the same way, with the same basic proportions and symmetry for over 1 million years. That's tradition. That's culture being passed down from generation to generation. Young Homo erectus individuals weren't figuring out how to make hand axes on their own. They were learning by watching adults, by copying, by being taught. That requires social learning abilities far beyond what we see in modern apes. But here's what's interesting. For all their sophistication compared to Oldowan tools, Acheulean hand axes don't show a lot of innovation. The design stays pretty much the same across vast stretches of time and space. A hand axe from Africa looks like a hand axe from India. One made 1 million years ago looks like one made 500,000 years ago. Compare that to modern human tools, which show rapid innovation and regional variation. Stone tool designs change every few thousand years, and different human populations develop distinctive styles. So Homo erectus had the cognitive ability for social learning and tradition, but maybe not for rapid innovation. They figured out something that worked and stuck with it, which, fair enough, if it ain't broke, don't fix it, right? A good hand axe could butcher an elephant, process plant materials, dig for tubers, scrape hides. Why mess with success? The sites where these tools are found tell us more about behavior. Some sites are kill sites or butchery sites, places where an animal carcass was processed. The pattern of cut marks on bones, the types of bones present, the association with tools, all of this suggests early humans were systematically dismembering animals and removing meat. Whether they were hunting or scavenging is still debated, and the answer probably varies by time and place. There's good evidence for scavenging. Many sites show carnivore tooth marks alongside human-made cut marks, suggesting humans were coming along after lions or hyenas had finished and taking what was left. Scavenging is actually a smart strategy if you don't have the physical tools to take down large game yourself. Wait for someone else to do the dangerous work, then move in with your tools and strip meat from the carcass, crack bones to access marrow that the primary predators couldn't get to. But there's also evidence suggesting at least some hunting. Spears, or possible spear points anyway, start appearing in the archaeological record by a few 100,000 years ago, and the types of animals found at some sites, the age profiles and body parts present, suggest deliberate hunting rather than opportunistic scavenging. Young animals and vulnerable individuals are overrepresented at some sites, which is what you'd expect if humans were selectively targeting easier prey. Probably they were doing both opportunistically. See a recently killed antelope with meat on it? Scavenge. Come across a herd and you've got a strategic advantage, like trapping them against a cliff or in a gully. Hunt. Early humans were flexible, taking meat however they could get it. This meat-eating had knock-on effects for social behaviour. If you've got a large animal carcass, you've got more food than one individual or even one family can consume before it spoils. Sharing makes sense. Bring it back to your group, distribute it, and you've just created social bonds, reciprocal obligations, maybe even rudimentary trade or gift-giving behaviours. Some sites show evidence of repeated use over time. These weren't temporary camps abandoned after one meal. These were places that hominin groups returned to regularly, perhaps seasonal aggregation sites where multiple families would meet up. Why gather in larger groups periodically? Probably the same reasons modern hunter-gatherers do. Exchange of mates to avoid inbreeding, sharing information about resources and dangers, social bonding and alliance building, maybe even trading of goods or materials. Fire sites add another dimension to understanding behaviour. We mentioned fire earlier, but let's dig deeper into what it meant for social life. Fire requires maintenance. Someone has to keep it burning, has to know where to find fuel, has to understand the dangers and how to control it. That's knowledge that needs to be taught and learned, another form of cultural transmission. And fire creates a focal point for social activity. You gather around the fire for warmth, for light, for cooking. It becomes a natural place for social interaction. Some anthropologists have suggested that sitting around fires at night, when you're not actively gathering food or watching for predators, that's when language really develops. You've got time for extended vocal communication, for storytelling, for teaching, for bonding. We can't know for sure what early Homo erectus sounded like or how sophisticated their language was. Their throat anatomy probably wouldn't have allowed the full range of sounds that modern humans make, but they clearly had communication beyond what apes have. Coordinating group activities, teaching tool making, maintaining fire, all of that requires some form of language, even if it's simpler than ours. Their brain anatomy gives us some clues. Parts of the brain associated with language and complex thought show expansion in Homo erectus compared to earlier hominins. Broca's area and Wernicke's area, the regions involved in language production and comprehension in modern humans, were more developed in Homo erectus than in Homo habilis. Does that mean they had language? Not necessarily. Those brain regions have other functions too, but it suggests they were moving in that direction. Social group size can be estimated from brain size using formulas developed by studying modern primates. Bigger brains generally correlate with larger social groups because you need more cognitive power to track relationships, remember who's who, navigate complex social hierarchies. For Homo erectus, the estimates suggest groups of maybe 70 to 100 individuals, similar to modern hunter-gatherer band sizes. Living in groups that large requires a lot of social intelligence. You need theory of mind, the ability to understand that others have thoughts and intentions different from your own. You need to remember past interactions, keep track of who helped you and who didn't. You need to cooperate with some individuals while competing with others. You need to form alliances, avoid conflicts, navigate relationships. All of that requires brain power. And if you're living in groups that large, you probably need rules, norms, cultural expectations about behaviour. Don't take someone else's food, share meat from big kills, respect dominance hierarchies, at least enough to avoid constant fighting, cooperate against external threats. These are the kinds of social norms we see in all human societies, and they probably have roots going back to Homo erectus or even earlier. Evidence of violence in the fossil record is rare but present. Some skulls show trauma that might be from interpersonal violence, though it's hard to distinguish weapon wounds from accidents or predator attacks. But humans are tribal, territorial, sometimes violent toward outsiders. Those tendencies probably have deep evolutionary roots. Competition between groups for resources, especially during times of scarcity, would have created selection pressure for both cooperation within groups and aggression toward outsiders. The geographic distribution of Homo erectus raises questions about population structure. Were populations in Africa still in contact with populations in Asia? Was there gene flow between regions, or were different populations evolving in isolation? The archaeological and fossil evidence suggests some isolation, with regional differences in anatomy and tool traditions, but there may have been occasional contact, migration, mixing of genes. Think about the distances involved. Walking from East Africa to China at an average pace might take months or years, depending on the route and how often you stop. That's not a journey an individual makes on purpose, but over generations, populations gradually expanding their range. It's totally feasible. And once established in Asia, Asian Homo erectus populations might have been relatively isolated from African populations for hundreds of thousands of years. What were they eating? Analyses of toothware, bone chemistry, archaeological remains all suggest a mixed diet. Plant foods still made up a large portion of calories, maybe most of them. Fruits, nuts, seeds, roots, tubers, leaves. But meat and animal fats became increasingly important, especially in temperate regions where plant foods might be scarce during winter months. The ability to eat a wide variety of foods was crucial for survival in diverse environments. Homo erectus in tropical Africa could rely on year-round plant productivity. Homo erectus in northern China had to deal with cold winters when plant foods were scarce. Having the cognitive ability and the tools to hunt or scavenge meat, to process frozen carcasses, to extract every possible calorie from their environment. That's what allowed them to survive in those challenging conditions. And then there's cooking. We talked about fire already, but cooked food deserves special attention because it's such a game changer. Cooking makes food easier to chew and digest. It breaks down tough fibers and makes nutrients more bioavailable. It kills parasites and bacteria, making food safer. And perhaps most importantly, it dramatically increases the caloric yield from food. Raw meat and plants require a lot of energy to digest. Your gut has to work hard to break down tough fibers and extract nutrients. Cooked food is essentially pre-digested. Your body can extract more calories with less effort. This meant Homo erectus could support their larger brains more efficiently. Remember, brains are energetically expensive. Cooked food helped pay that cost. There's a hypothesis that cooking and brain expansion are linked in a positive feedback loop. Cooking allows bigger brains. Bigger brains allow better food acquisition and preparation, including more sophisticated cooking, which allows even bigger brains. Round and round, driving the increase in brain size we see over the last million years. But controlled fire doesn't show up unambiguously in the record until several 100,000 years ago, so either Homo erectus was getting by without cooking for a long time, or they were using fire but not leaving clear archaeological traces. Fire sites are hard to identify in the fossil record, especially older ones. Wood ash degrades, fire hearths get disturbed, It's possible Homo erectus was using fire earlier than we can prove. We just haven't found clear evidence yet. What about shelter? Evidence is scarce because organic materials don't preserve well. We've got some possible structures like that stone circle at Olduvai that might have supported a windbreak. Later sites in Europe show more definitive evidence of shelter construction. But for early Homo erectus, we're mostly speculating based on what would have been necessary for survival. In tropical and subtropical regions, shelter might not have been critical. A simple windbreak, an overhang, a spot under a tree might suffice, but in temperate regions with cold winters, Homo erectus would have needed protection from the elements. Whether they were building structures, using caves, or just huddling around fires, we can't say for sure, but they survived in those environments, so they must have figured something out. Clothing is another mystery. No direct evidence survives, of course, but in cold climates, some form of body covering would have been necessary. Animal hides, possibly scraped and prepared using stone tools, would be the obvious choice. By the time Homo erectus reached northern China, they must have had some way to keep warm, and clothing is the most likely explanation. These behavioral adaptations, tools, fire, possibly clothing, possibly shelter, these are examples of cultural evolution beginning to outpace biological evolution. Instead of evolving thicker fur genetically, humans used animal hides. Instead of evolving bigger teeth for tough foods, they used tools to process food. Instead of evolving to run faster to escape predators, they cooperated in groups and used weapons for defense. This ability to solve problems through culture rather than biology is the defining characteristic of humans, and it started with species like Homo erectus, maybe even earlier. It's why humans are so adaptable, why we've spread to every environment on Earth, why we've become the dominant species on the planet. We don't need to wait for natural selection to slowly modify our bodies over thousands of generations. We can invent solutions, share them through teaching and culture, and adapt to new challenges within a single generation. Homo erectus wasn't thinking about any of this in abstract terms. They weren't trying to be the progenitors of human culture. They were just living their lives, solving immediate problems, passing on knowledge to their offspring. But in doing so, they established patterns that would define human existence for the next million years and beyond. Tool making, fire use, social cooperation, cultural transmission, flexible problem solving. These are the foundations on which all later human success was built. Homo erectus had a good run, over 1.5 million years of success, but evolution doesn't stop just because a species is doing well. Populations adapt to local conditions, geographic isolation leads to divergence, and eventually you end up with enough accumulated changes that you're looking at new species. By around 600,000 years ago, that's exactly what was happening. Homo erectus in different parts of the world was evolving into new forms. In Africa, populations were developing larger brains and more sophisticated tool technologies. By around 700,000 to 300,000 years ago, fossils appear that are transitional between Homo erectus and what would become anatomically modern humans. Some scientists lump these together under the name Homo heidelbergensis, though that name is controversial and may actually represent several different species or populations. Homo heidelbergensis fossils have been found across Africa, Europe, and Western Asia. They had larger brains than earlier Homo erectus, averaging around 1,200 cubic centimeters, getting close to modern human brain size. Their skulls still had prominent brow ridges and thick bones, but their faces were less projecting, more modern looking in some ways. These weren't just bigger-brained Homo erectus, though. Their tools were more sophisticated. They were making refined hand axes, spears with carefully shaped points, possibly even using hafting techniques to attach stone points to wooden handles. Their hunting abilities appear to have been much better than earlier humans. Evidence from sites in Europe shows organized hunting of large game like horses and elephants. And speaking of Europe, that's where things get really interesting. European populations of Homo heidelbergensis living in a cold, challenging environment started developing their own unique characteristics. By around 400,000 years ago, these populations were on the evolutionary path that would lead to Neanderthals, Homo neanderthalensis, one of our closest extinct relatives. Neanderthals deserve their own documentary series, honestly. They were remarkably sophisticated humans who thrived in Ice Age Europe for hundreds of thousands of years. Stocky and muscular, adapted to cold climates, with brains actually slightly larger on average than modern humans. They made complex tools, used fire extensively, built shelters, buried their dead, possibly even had forms of art and symbolic behaviour. But we're getting ahead of ourselves, because while all this was happening in Europe, in Africa, different populations of Homo heidelbergensis, or whatever we want to call them, were evolving in a different direction, and that direction led to us, Homo sapiens, anatomically modern humans. The transition to modern humans happened sometime around 300,000 years ago, maybe a bit earlier. The fossil evidence is fragmentary and debated, as usual. There are fossils from Jebel Irhoud in Morocco, dated to around 315,000 years ago, that show a mix of modern and archaic features. Modern-looking face and teeth, but still a somewhat elongated skull shape. Are these the earliest Homo sapiens, or something transitional? Depends who you ask. What's clear is that by 200,000 years ago, fossils from Ethiopia show fully modern human anatomy. Rounded skulls, small brow ridges, prominent chins. If you cleaned up one of these individuals and put them in modern clothes, they'd blend right into a crowd today. Anatomically, they were us. But here's the weird thing. Despite having modern anatomy, these early Homo sapiens didn't have obviously modern behaviour. Their tools were still similar to what earlier humans were making. There's no clear evidence of art, symbolism, complex social organisation, none of the things we associate with modern human culture. The hardware was there, the big modern brain was there, but the software hadn't been installed yet. It wasn't until much later, maybe 70,000 to 50,000 years ago, that we see clear evidence of modern human behaviour emerging. Art, personal ornaments, complex tools made from bone and antler, long-distance trade networks, sophisticated hunting strategies. This is sometimes called the Upper Paleolithic Revolution or the Great Leap Forward, and it represents a massive increase in cultural sophistication. What caused it? Maybe brain structure finally reached a critical threshold. Maybe language became fully developed. Maybe population density increased to the point where cultural innovations could spread and accumulate. Maybe it was a combination of all these factors and more. We don't really know. But something happened that allowed human culture to take off in ways that earlier humans, despite similar brain sizes, hadn't achieved. Meanwhile, back in Africa, where modern humans were evolving, we weren't alone. Different archaic human species were still around. Homo erectus populations persisted in some areas. Those robust Australopithecines were finally gone, but other hominins filled various ecological niches. Africa, from 500,000 to 50,000 years ago, was home to multiple human species, possibly interacting, possibly competing, maybe occasionally interbreeding. We know interbreeding happened with Neanderthals and another group called Denisovans because modern humans outside of Africa carry small percentages of their DNA. When Homo sapiens migrated out of Africa starting around 70,000 to 60,000 years ago, they encountered these other human species in Eurasia and mixed with them. So if you're of European or Asian descent, you've got a bit of Neanderthal in your family tree. People of Melanesian descent have both Neanderthal and Denisovan ancestry. The Denisovans are particularly mysterious because we only have a handful of fossils from them, a finger bone, some teeth, a jawbone, but their DNA, extracted from those fragments, tells us they were a distinct population related to Neanderthals but genetically separate. They ranged across Asia and possibly into Southeast Asia and Oceania. Beyond that, we know almost nothing about what they looked like or how they lived. There's also growing evidence for other archaic human populations in Africa that contributed DNA to modern humans. Ghost populations, they're sometimes called, because we don't have fossils, but we can detect their genetic signatures in living people. These might be late surviving populations of Homo heidelbergensis or something similar that interbred with early Homo sapiens. This genetic evidence completely changed how we think about human evolution. It's not a clean story of one species replacing another. It's messy, with interbreeding and gene flow between populations, hybrid individuals, complex branching and merging of lineages. The family tree is less of a tree and more of a braided stream, with channels splitting and rejoining. What happened to all these other human species? Why are they extinct while we're still here? There's no simple answer. Climate change probably played a role. The Pleistocene was a time of dramatic climate fluctuations, with ice ages coming and going. Species adapted to specific environments would have been vulnerable when those environments changed. Competition with Homo sapiens probably mattered too. If two species are competing for the same resources, the one with superior technology, better social organization, or more flexible behavior is going to have an advantage, not necessarily through violence, though that might have occurred, but just through being able to exploit resources more efficiently. There's also the possibility of diseases. When populations that had been separated for hundreds of thousands of years suddenly come into contact, they're exposed to pathogens they have no immunity to. Could Homo sapiens have carried diseases that decimated Neanderthal or Denisovan populations? It's possible, though we have no direct evidence. Population size might have been a factor too. Small populations are vulnerable to inbreeding, genetic drift, random disasters that could wipe them out. If Neanderthals and Denisovans were living in relatively small, isolated groups, while Homo sapiens populations were larger and more connected, that demographic advantage alone could explain why we persisted and they didn't. Or maybe it was just random chance. Evolution isn't teleological. There's no reason Homo sapiens had to be the lineage that survived. Under slightly different circumstances, we might have gone extinct and Neanderthals might be the ones building cities and launching rockets. The fact that we're here and they're not doesn't necessarily mean we were superior. We got lucky. What's undeniable is that by about 30,000 years ago, we were the only human species left. Neanderthals disappeared around this time. Denisovans probably did too, though the dates are uncertain. Late surviving Homo erectus populations in Indonesia were gone. Homo floresiensis, those tiny humans from Flores Island that some call hobbits, they went extinct around 50,000 years ago. For the first time in millions of years, there was only one hominin species walking the earth, us, and we proceeded to spread into every inhabitable environment, from Arctic tundra to tropical rainforests to island chains to eventually, in the last few thousand years, every continent except Antarctica. This expansion was driven by cultural and technological innovation. By this point, humans had sophisticated language, allowing complex communication and planning. We had art and symbolism, enabling abstract thought and shared belief systems. We had improved tool technologies, including specialized tools for different tasks. We had better hunting weapons like atlatls and eventually bows and arrows. We had tailored clothing, sophisticated shelter construction, watercraft for crossing bodies of water. Each innovation opened up new possibilities. Tailored clothing meant we could survive in colder climates. Watercraft meant we could reach islands and cross rivers. Better hunting weapons meant we could take down larger game more safely. And all of this knowledge was transmitted culturally, taught to the next generation, refined and improved over time. By 10,000 years ago, some human populations were beginning to transition from hunting and gathering to agriculture. This was arguably an even bigger revolution than the emergence of modern behavior 50,000 years earlier. Agriculture meant settled communities, population growth, eventually cities and civilizations and writing and all the rest. But that's well beyond the scope of early human evolution. The point is, the trajectory was set. Once hominins crossed certain thresholds, bipedalism, tool use, larger brains, complex language, cultural transmission, the stage was set for everything that followed. Looking back across the 7 million years or so since our lineage split from the ancestors of chimpanzees, the pattern is clear. Lots of experimentation, lots of branches on the family tree, most going extinct, but the successful lineages shared certain traits: adaptability, behavioral flexibility, intelligence, social cooperation, the ability to learn and transmit culture. Early hominins like Australopithecus afarensis perfected bipedalism, freeing our hands. Early Homo species like Homo habilis developed bigger brains and basic tool use. Homo erectus took those traits and ran with them, literally spreading across continents. Later species like Homo heidelbergensis and eventually Homo sapiens pushed brain size and cultural sophistication even higher. None of these species were trying to evolve toward anything. They were just living, surviving, reproducing. But the cumulative effect of millions of years of small changes, of natural selection favoring certain traits, of cultural evolution accelerating biological evolution, all of that led to us, a species capable of understanding our own origins, of piecing together our evolutionary history from fragments of bone and stone. It's a remarkable story, made all the more remarkable by the fact that we can tell it. Every fossil we find, every stone tool we analyze, every genetic sequence we decode adds another piece to the puzzle. The picture will never be complete. Too much has been lost to time. But what we have is enough to see the broad outline, to understand the major transitions, to marvel at the journey from bipedal apes in Africa to humans capable of reshaping the planet. And it all started with creatures not so different from Lucy, walking upright through the African landscape 3 million years ago, just trying to make it through another day. They had no idea where their descendants would end up. How could they? But their success, their survival, their gradual evolution over countless generations, that's what made everything else possible. That's what made us possible. After millions of years of evolution, after countless species trying different strategies for survival, after dramatic climate changes and continental migrations and interbreeding and extinction, here we are, the only surviving hominin species. But what does it actually mean to be human? What makes us different from all those other species that came before, including the ones we coexisted with? This isn't just an academic question. It goes to the heart of how we see ourselves, how we think about consciousness and intelligence, how we decide who or what deserves moral consideration, and the answers keep changing as we learn more about our extinct relatives. For a long time, we thought tool use was the defining human characteristic. Humans make tools, animals don't, case closed. But then we found that chimps use tools, crows use tools, even octopuses use tools, and we discovered that Australopithecines and maybe even earlier hominins were making stone tools. So tool use alone doesn't separate us from the animal kingdom or even from earlier hominins. Okay, what about language? Surely complex language is uniquely human, and it's true that human language is more sophisticated than animal communication systems. We have grammar, syntax, the ability to talk about abstract concepts and things that don't exist. But Neanderthals probably had language. Homo heidelbergensis might have. Even Homo erectus might have had some form of proto-language. So language isn't unique to Homo sapiens either, at least not in a simple binary way. Culture, then, the ability to transmit knowledge across generations through teaching and learning. But again, Neanderthals had culture. They made sophisticated tools, buried their dead, created art. Homo erectus had cultural traditions in tool-making that persisted for hundreds of thousands of years. Even some modern apes show rudimentary cultural behaviours. Art and symbolism. The archaeological record shows that earlier humans and even other species might have had some forms of symbolic behaviour. Neanderthals made jewellery and possibly painted cave walls. Homo erectus shells from Indonesia have geometric engravings that might be deliberate art. Self-awareness, theory of mind, moral reasoning, these are harder to detect in the fossil record, but there's no reason to think we're the only species that ever had them. Caring for injured or elderly group members, which we see evidence for in earlier human species, requires empathy and social cognition. The more we learn, the fuzzier the boundary between human and not human becomes. We want there to be some bright line, some special quality that separates us from everything else. But evolution doesn't work that way. Every trait we have is built on traits our ancestors had. Every capability we possess emerged gradually from simpler versions in earlier species. Maybe the difference isn't in any single trait, but in the combination and degree. Yes, other species use tools, but our technology is orders of magnitude more complex. Yes, other species communicate, but our language is exponentially more flexible and powerful. Yes, other species have culture, but ours is incomparably richer and more varied. Or maybe the real difference is in cumulative culture. Most animals and even earlier humans could learn and transmit knowledge, but it didn't accumulate much over generations. Each generation started almost from scratch, maybe with a few more tricks than the previous one. Modern humans are different. We build on what came before. Each generation adds to the collective knowledge, and it snowballs. That's why human progress accelerated so dramatically in the last 50,000 years, and especially in the last 10,000. We're not smarter as individuals than Neanderthals or early Homo sapiens, but we're building on 200,000 years of accumulated knowledge and cultural evolution. We're standing on the shoulders of thousands of previous generations. This cumulative culture is possible because of complex language, which allows precise transmission of information, and because of external memory systems like writing, which we only invented about 5,000 years ago, but which completely transformed what's possible for humans to know and do. The story of human evolution also raises questions about ethics and morality. If Neanderthals had language, culture, art, social bonds, everything we associate with being human, were they people? Do we owe them moral consideration in how we talk about them and study them? If we could bring them back through some future genetic technology, would they have rights? these aren't just thought experiments. They have practical implications for how we think about other intelligent species, including potentially artificial intelligences or enhanced animals that we might create in the future. Where do we draw the line for personhood? What cognitive or behavioral thresholds need to be crossed? And what about the future of human evolution? Are we still evolving? The answer is yes, technically. Any population that reproduces will experience evolution. But the forces shaping human evolution today are very different from those that shaped our ancestors. Natural selection pressures are weaker in modern human societies. We have medicine, so traits that would have been lethal in the past might persist. We have technology to compensate for physical limitations. We have agriculture and food systems, so we're not selecting for the most efficient hunters or gatherers. We have contraception and choose when and how many children to have, which changes reproductive success patterns. But we're also facing new selection pressures. Disease resistance matters differently now that we live in dense populations with global travel. Ability to tolerate modern diets high in processed foods might be under selection. Tolerance for pollutants and environmental toxins could become selective factors. And then there's the possibility of directed evolution through technology. Gene editing, genetic engineering, cybernetic enhancements, all of these could allow humans to guide their own evolution intentionally rather than leaving it to random mutation and natural selection. Whether that's a good idea is a whole other ethical debate. Looking even further ahead, what if humans colonize other planets? Populations living in different environments on Mars or space stations or exoplanets would face different selection pressures. Given enough time and isolation, they could diverge into separate species, just like Homo erectus populations diverged in Africa, Europe, and Asia. But we might also merge rather than diverge. Global travel and communication mean human populations are more mixed now than they've been for thousands of years. Regional genetic differences are decreasing. We might be moving toward becoming more genetically homogeneous rather than more diverse. The deep lesson from studying human evolution is that we're not separate from nature. We're part of it. We're the product of the same evolutionary processes that created every other living thing. We're not the goal or end point of evolution. We're just one branch on the tree of life that happened to survive while our cousin species didn't. That should give us humility. We're not inherently superior to Neanderthals or Denisovans or Homo erectus. We got lucky in some ways. We happened to have the right traits at the right time in the right places. Under different circumstances, it could easily have been a different species that survived and we'd be the extinct ones. But it should also give us confidence. We come from a lineage that has been solving problems and adapting to challenges for millions of years. Our ancestors survived ice ages, droughts, predators, diseases, competition from other species. They figured out how to make tools, control fire, hunt, gather, cooperate in groups. That resilience and adaptability is in our genes and our culture. Understanding our evolutionary history also helps us understand ourselves in the present. Why do we have certain instincts and biases? Why are we tribal and territorial? Why do we form tight social bonds? Why are we so good at pattern recognition and problem solving, but also prone to cognitive errors? Evolution shaped our minds for survival in Pleistocene environments, and we're still carrying that psychological baggage even though our world looks nothing like the African savanna where our ancestors evolved. This can help explain human behavior without excusing it. Yeah, we evolved to be wary of outsiders because that helped our ancestors survive, but we can recognize that instinct and choose not to act on it. We're not slaves to our evolutionary past. We have the cognitive capacity to understand our own nature and choose to be better. The quest to understand human origins is ongoing. Every few years, new fossils are discovered that change what we thought we knew. New techniques like ancient DNA analysis, high-resolution CT scanning, isotope analysis, they're revealing details that previous generations of scientists couldn't access. We're finding new hominin species like Homo naledi in South Africa or Homo luzonensis in the Philippines that add even more complexity to the story. And there are still huge gaps in our knowledge. We don't know who the common ancestor of humans and chimps was. We don't have good fossils from crucial time periods. We don't know exactly how language evolved or when. We don't understand all the environmental pressures that drove human brain expansion. We're still debating basic questions like how many species of early Homo there were and how they're related to each other. But that's what makes it exciting. The story isn't finished. Every new discovery has the potential to rewrite parts of it, and as techniques improve and we find more fossils, we'll fill in more of those gaps. Maybe in another 50 years, we'll have answers to questions that seem insoluble now. What we do know is enough. We know that we evolved from ape-like ancestors in Africa. We know that bipedalism came first, before big brains. We know that tool use and meat-eating were important in our evolution. We know that fire changed everything. We know that humans spread across the world and adapted to countless different environments. We know that we weren't alone, that multiple human species existed and sometimes interacted. And we know that we're the product of millions of years of small changes, each generation slightly different from the last, adaptive pressures selecting for certain traits, lucky breaks and random events shaping outcomes. We're not separate from nature or exempt from its rules. We're part of the great story of life on Earth, one thread in the vast tapestry of evolution. That story includes triumph and tragedy. Triumph in the sense that our lineage survived and thrived against incredible odds. Tragedy in the sense that countless other species, including our closest relatives, went extinct. The hominin family tree is mostly dead branches. We're the one twig that's still growing, and there's no guarantee we'll continue to. Because here's the thing about being the last surviving hominin. There's no backup. If we screw this up, if we destroy our environment or blow ourselves up or fail to adapt to changing conditions, there's no other human species waiting in the wings to take over. We're it. The responsibility for the future of intelligent life on Earth, at least the human variety, rests entirely with us. That's a sobering thought, but it's also empowering. We have the knowledge, the technology, the cultural systems to address the challenges we face. We can choose to be wise, we can choose to learn from our history, to understand our nature, to work together to build a sustainable future. Our ancestors couldn't do that. They didn't have the luxury of understanding evolution or climate science or ecology. They were just trying to survive day to day, but they succeeded generation after generation, passing on their genes and their knowledge to their descendants, and eventually their descendants became us. We owe them something, those millions of anonymous ancestors who walked upright, made tools, controlled fire, painted caves, told stories around hearths, passed down knowledge. They survived so we could exist. The least we can do is try to be worthy of that legacy, to be good ancestors for future generations. The story of human evolution isn't really about the past. It's about the present and the future. It's about understanding where we came from so we can better understand where we're going. It's about recognizing our place in nature, our connection to all life on Earth, our responsibility to the planet and to future generations. From Lucy walking through the African landscape 3 million years ago to humans walking on the moon in 1969, from crude stone choppers to quantum computers, from small groups of apes struggling to survive to a global civilization of 8 billion people. That's the arc of human evolution, and we're living through a critical chapter of it. What we do now matters. The choices we make, the knowledge we gain, the values we choose to uphold, they'll shape the future of our species. We're not the end point of human evolution. We're somewhere in the middle of the story, and the next chapters, those are up to us to write.